Welcome to Tech with Kaushik. This is set 23 of our DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. Choose your answer before the timer ends. Then review the correct answer, detailed explanation, and exam tip. Keep track of your score and see how exam ready you are. Each practice set is completely standalone, so you can start here without watching any of the other sets first. Playlist link in the description. Let us begin set 23. Question number 412. Let's go. The topic for this question is deployment strategies. Scenario. A company runs a mission-critical REST API on Amazon Elastic Container Service, Amazon ECS. The company wants to implement automated rollback capabilities during new application deployments. Before routing 100% of production traffic to a new ECS task set, the deployment pipeline must execute simulated user journeys against the newly deployed version. If the API responses are slow or return HTTP 500 errors, the deployment must automatically abort and instantly shift all traffic back to the original version. Which solution meets these automated validation and rollback requirements with the least operational overhead? Options. Option A. Deploy the ECS service using AWS Code Deploy Blue/Green deployments with an application load balancer test listener for the replacement task set. Configure an after-allow test traffic Lambda validation hook to execute the simulated user journeys against the test listener and fail the deployment if latency or HTTP 500 checks fail. Enable automatic rollback for failed deployments and relevant CloudWatch alarms. Option B. Configure Amazon CloudWatch application insights to monitor the ECS cluster. Create an Amazon Event Bridge rule that triggers an AWS Lambda function if application insights detects anomalous HTTP 500 errors. Program the Lambda function to call the ECS Update Service API to revert the task definition. Option C. Deploy the service using an AWS CloudFormation Stack update. Use an AWS Step Function State Machine to invoke AWS X-ray tracing against the new containers. If tracing reveals latency, the state machine triggers a CloudFormation Stack rollback. Option D. Implement a canary deployment using Amazon Route 53 weighted routing. Send 10% of traffic to the new version. Configure AWS WAF to monitor the error rate on the new target group and automatically adjust the Route 53 weights if errors spike. The answer here is Option A. Deploy the ECS service using AWS Code Deploy Blue/Green deployments with an application load balancer test listener for the replacement task set. Configure an after-allow test traffic Lambda validation hook to execute the simulated user journeys against the test listener and fail the deployment if latency or HTTP 500 checks fail. Enable automatic rollback for failed deployments and relevant CloudWatch alarms. This works because for an ECS Blue/Green deployment, Code Deploy can route test traffic through a dedicated test listener to the green replacement task set before production traffic is shifted. An after-allow test traffic lifecycle hook can invoke a Lambda validation function that exercises the new version and reports success or failure to Code Deploy. A failed validation hook can stop the deployment and trigger automatic rollback, while CloudWatch alarms can provide additional rollback signals for latency or HTTP errors. B. This replaces native deployment validation and rollback with custom event bridge/Lambda orchestration after an anomaly is detected. C. CloudFormation and step functions do not provide the native ECS Blue/Green test traffic lifecycle and rollback integration described in the requirement. D. AWS WAF is not an application performance controller and does not automatically change Route 53 weights based on target group latency or HTTP 500 rates. Here's a useful exam tip. For ECS Code Deploy Blue/Green validation before production traffic, use a test listener and the after-allow test traffic lifecycle hook. A failed hook can trigger rollback before full traffic shifting. Next up is question number 413. A company operates a legacy monolithic application running on Amazon EC2 Linux instances. The development team wants to gain deeper visibility into internal application performance, specifically the API request duration and internal database query latency. The team has modified the application code to generate these metrics locally in StatsD format. A DevOps engineer needs to transport these custom metrics into Amazon CloudWatch. Which solution will achieve this with the least operational overhead? Choice A. Create an AWS Lambda function that uses AWS Systems Manager Run command to periodically execute a shell script on the EC2 instances, parse the statsd output, and call the putMetricData API. Choice B. Install and configure the unified Amazon CloudWatch agent on the EC2 instances. Configure the agent to listen for statsd metrics on a local port and automatically forward them to CloudWatch. Choice C. Configure the application to write the metrics to a local log file. Use Amazon Kinesis Data Promptail to tail the file and stream the data into Amazon Managed Service for Prometheus. Choice D. Install AWS IoT Greengrass on the EC2 instances. Create a local component that intercepts the statsd metrics and uses MQTT to publish them to an AWS IoT core topic integrated with CloudWatch. The right response is option B. Install and configure the unified Amazon CloudWatch agent on the EC2 instances. Configure the agent to listen for statsd metrics on a local port and automatically forward them to CloudWatch. Let's look at the reasoning. The unified Amazon CloudWatch agent natively supports collecting custom metrics using the statsd and collective protocols. By running the agent locally on the EC2 instances and configuring it to listen for statsd packets, the application can simply send metrics over localhost. The agent handles batching, signing, and securely transmitting the metrics to CloudWatch using the putMetricData API automatically. The other choices do not work because A. Creating a custom Lambda function to remotely SSH/SSM into instances, parse logs, and push metrics is highly inefficient, fragile, and requires significant custom coding. C. Promptail is an agent used to forward logs to Grafana Loki, not Amazon Managed Service for Prometheus. Prometheus typically uses scraping, pull model, or the AWS distro for OpenTelemetry. D. AWS IoT Greengrass is designed for edge and IoT devices. While it could theoretically be forced onto EC2, it is vastly more complex than the standard CloudWatch agent designed exactly for this purpose. The main takeaway is the unified Amazon CloudWatch agent is the standard, lowest overhead AWS solution for collecting system-level metrics, log files, and custom application metrics via statsd or collected from EC2 instances. Question number 414. A company runs a stateless web application hosted on an Amazon EC2 auto-scaling group behind an application load balancer, ALB. The development team has released a major UI overhaul and wants to test it in production. To mitigate risk, the team wants to direct exactly 10% of real user traffic to the new UI version, while the remaining 90% of traffic continues to route to the stable, existing version of the application. Which solution will implement this canary testing strategy with the least number of configuration changes? Option A. Deploy the new UI to a separate AWS account. Use Amazon Route 53 cross-account weighted routing records to send 10% of the domain's traffic to the new ALB and 90% to the existing ALB. Option B. Launch a new auto-scaling group for the new UI and register it to a new ALB target group. Modify the existing ALB listener rule to forward traffic to both target groups, assigning a weight of 90 to the existing target group and 10 to the new target group. Option C. Containerize the application and deploy it to Amazon Elastic Container Service, Amazon ECS. Configure AWS Code Deploy to manage the deployment using the Code Deploy default, the ECS Canary 10%, 5 minutes deployment configuration. Option D. Refactor the application code to check an AWS AppConfig feature flag. Configure AppConfig to randomly serve the enable new UI equals true flag to 10% of the EC2 instances based on their instance IDs. Go with option B. Launch a new auto-scaling group for the new UI and register it to a new ALB target group. Modify the existing ALB listener rule to forward traffic to both target groups, assigning a weight of 90 to the existing target group and 10 to the new target group. Application load balancers, YLBs, natively support weighted target groups. By modifying the listener rule to forward traffic across two target groups, the ALB handles the traffic splitting, 90/10, directly at the application layer. This requires the fewest configuration changes as it avoids DNS changes, custom deployment controllers, or application refactoring. Now let's rule out the other options. A. Route 53 weighted routing operates at the DNS layer. DNS caching by client browsers and ISPs makes a precise 10% traffic split unreliable compared to ALB-weighted target groups. C. Containerizing the application and migrating it to Amazon ECS is a massive architectural change, directly violating the requirement for the least number of configuration changes. D. Refactoring the application code to use app-config feature flags requires development effort and modifying the application logic, which represents significantly more operational overhead than updating a load balancer rule. Keep this point in mind for the exam. When you need to precisely shift a percentage of traffic between EC2 autoscaling groups without changing the architecture, use ALB-weighted target groups. Next, question number 415. Scenario. A company uses AWS CloudFormation to manage its infrastructure. Currently, a DevOps team manually uploads modified CloudFormation templates to an Amazon S3 bucket, which triggers an AWS code pipeline to deploy the stack updates. Recently, several misconfigured templates were deployed to production, causing resource outages. The team struggled to identify what changed and revert the templates quickly. The operations manager mandates that all infrastructure changes must now be version controlled, and a peer must review and approve the exact code modifications before any deployment occurs. Which solution will enforce these controls with the least operational overhead? Choices. Option A. Store the CloudFormation templates in an AWS code commit repository. Update the pipeline source action to use the repository. Insert a manual approval action in code pipeline immediately before the CloudFormation deploy action. Option B. Migrate the CloudFormation templates to a Git repository using AWS code connections. Configure AWS CloudFormation Git sync. Require developers to submit pull requests for template changes, leveraging the Git provider's native PR review and approval workflow to trigger deployments. Option C. Store the templates in Amazon S3. Enable S3 versioning. Create an Amazon Event Bridge rule that triggers an AWS step functions workflow whenever an object is updated. Use the workflow to send an email to the operations manager for approval before calling the CloudFormation API. Option D. Create a pre-deployment AWS Lambda function within code pipeline that parses the CloudFormation template using a static analysis tool. If the tool detects extensive modifications, the function pauses the pipeline and sends an Amazon SNS notification for review. In this case, choose option B. Migrate the CloudFormation templates to a Git repository using AWS code connections. Configure AWS CloudFormation Git sync. Require developers to submit pull requests for template changes, leveraging the Git provider's native PR review and approval workflow to trigger deployments. Here's why. AWS CloudFormation Git sync automates the deployment of CloudFormation stacks directly from a Git repository, GitOps. By adopting Git, the team gains native version control. Changes are proposed via pull requests, PRs, allowing peers to review the exact code diff before approval. Once the PR is merged, CloudFormation Git sync automatically deploys the update. This eliminates the need to maintain an intermediate code pipeline entirely. The remaining options can be eliminated because while code pipeline with a manual approval action works, reviewing infrastructure diffs in a pipeline interface is clunky compared to native Git pull requests. CloudFormation Git sync removes the pipeline maintenance overhead completely. C. Using Event Bridge and step functions to orchestrate deployments from S3 is a complex custom pipeline build that ignores modern GitOps practices. D. Writing custom Lambda scripts to perform static analysis and conditionally pause pipelines is extremely high overhead and complex to maintain. AWS CloudFormation Git sync, GitOps, is the modern, lowest overhead approach to synchronizing infrastructure deployments with version control, leveraging native Git pull request workflows for peer review. Question number 416. The focus now shifts to high availability. Here's what is happening. A media company hosts a static image portfolio in an Amazon S3 bucket located in the East 1 region. Users globally complain about slow image loading times. Furthermore, the company's disaster recovery policy requires that the static assets remain highly available even if the primary S3 bucket becomes inaccessible due to a region-wide issue. Which solution will accelerate global content delivery and provide cross-region high availability with the least operational effort? Review the options. Option A. Enable Amazon CloudFront with Origin Shield in East 1 Configure an origin group with the primary S3 bucket in US, East 1, and a secondary S3 bucket in EU, West 1. Enable S3 cross-region replication from the primary to the secondary bucket. Option B. Deploy AWS Global Accelerator. Configure endpoint groups in US, East 1, and EU, West 1 targeting separate S3 buckets. Use AWS Data Sync on an hourly schedule to synchronize images between the two S3 buckets. Option C. Set up two separate Amazon CloudFront distributions, one connected to an S3 bucket in US, East 1, and one to an S3 bucket in EU, West 1. Use an Amazon Route 53 latency-based routing policy to direct users to the fastest distribution. Option D. Deploy a fleet of Amazon EC2 instances in multiple regions running varnish cache in front of the S3 bucket. Configure Amazon Route 53 geolocation routing to direct users to the closest caching instance. The best choice is Option A. Enable Amazon CloudFront with Origin Shield in US, East 1. Configure an origin group with the primary S3 bucket in US, East 1, and a secondary S3 bucket in EU, West 1. Enable S3 cross-region replication from the primary to the secondary bucket. This is the best choice because this solution leverages native AWS Edge services for both performance and resilience. CloudFront accelerates global delivery by caching images at edge locations. Origin Shield further reduces load on the primary S3 bucket. Configuring a CloudFront origin group provides automatic, seamless failover. If the primary US East 1 bucket returns a 5xx error, CloudFront instantly attempts to fetch the object from the secondary EU West 1 bucket. S3 replication keeps the buckets synchronized. Let's quickly check the incorrect choices. B. AWS Global Accelerator does not cache content. It optimizes network paths. Data sync runs on a schedule, minimum hourly, and is not intended for continuous S3 replication, meaning failovers would result in stale data. C. Setting up two separate CloudFront distributions with Route 53 latency routing splits the cache, reducing hit rates and increasing origin load, and does not provide seamless object-level failover. D. Deploying EC2 instances running varnish cache introduces immense operational overhead, patching, scaling, managing varnish, when CloudFront provides managed global caching natively. Exam tip. To provide highly available, cross-region failover for Amazon CloudFront behind a single distribution, configure a CloudFront origin group targeting two synchronized S3 buckets. Question number 417. Let's go. A DevOps team uses the AWS Cloud Development Kit, AWS CDK, in TypeScript to manage a serverless application. The architecture includes Amazon API Gateway, AWS Lambda, and Amazon DynamoDB. The team must deploy this exact architectural pattern across three distinct environments, development, staging, and production, in the same AWS account. While the core architecture is identical, specific parameters, such as the database read capacity and the API rate limits, must differ depending on the target environment. The team wants to minimize code duplication. Which approach meets these requirements with the least development overhead? Choices. Option A. Compile the TypeScript CDK code into an AWS CloudFormation template. Use the CloudFormation template to create an AWS Service Catalog product. Provision the product 3 times, using CloudFormation parameters to override the environment-specific values. Option B. Author custom level 3, L3, CDK constructs that combine the API Gateway, Lambda, and DynamoDB resources. Define a single CDK stack class that accepts an environment configuration object as a property. Instantiate this stack class 3 times in the CDK app, passing the respective configuration for development, staging, and production. Option C. Create a distinct custom level 1, L1, CDK construct for each environment. Hardcode the environment-specific configurations directly into the constructs. Use the CDK CLI context flag to specify which construct to synthesize during deployment. Option D. Define the infrastructure using AWS CDK Level 2, L2, constructs. Write a bash script that uses sed to find and replace configuration values in the TypeScript source code before executing the CDK deploy command for each environment. The right response is option B. Author custom level 3, L3, CDK constructs that combine the API Gateway, Lambda, and DynamoDB resources. Define a single CDK stack class that accepts an environment configuration object as a property. Instantiate this stack class 3 times in the CDK app, passing the respective configuration for development, staging, and production. The main reason is in the AWS CDK, level 3, L3, constructs are designed specifically to encapsulate architectural patterns, combining multiple L2 resources into reusable components. By defining a single CDK stack that takes properties for environment configuration, you maximize code reuse. In the main CDK application entry point, you instantiate this single stack class 3 times, once for each environment, passing the unique variables, for example, table capacities. Here's why the alternatives are not suitable. A. Compiling CDK to CloudFormation to use AWS Service Catalog abandons the benefits of deploying and managing state directly through the CDK CLI, introducing unnecessary steps. C. Creating separate L1 constructs, raw CloudFormation resources, for every environment results in massive code duplication and violates the requirement to minimize overhead. D. Using SED to find and replace values in code before deployment is a fragile, outdated scripting anti-pattern. CDK natively supports passing configuration properties to stacks. A helpful shortcut is this. In the AWS CDK, create level 3, L3, constructs to abstract multi-resource architectural patterns. To deploy to multiple environments, instantiate the same stack class multiple times with different configuration properties within the CDK app. Now for question number 418. Next, let's move into artifact management. Here's the scenario. A company builds its application as a Docker container image multiple times a day and pushes the images to an Amazon Elastic Container Registry, Amazon ECR, repository. Over time, the repository has accumulated thousands of untagged images from intermediate builds and older tagged images that are no longer deployed. To reduce storage costs, a DevOps engineer needs to automatically delete all untagged images older than 14 days and keep only the 50 most recent tagged images. Which solution will accomplish this with the least operational overhead? The choices are: Option A. Write an AWS Lambda function that uses the AWS SDK describe images and batch delete image AP is to evaluate and remove old images. Schedule the function to run daily using Amazon Event Bridge. Option B. Configure an Amazon S3 lifecycle policy on the backend S3 bucket that AWS utilizes to store the EC or image layers, setting the expiration action to 14 days for untagged objects. Option C. Create an Amazon EC or lifecycle policy containing 2 rules. One rule to expire untagged images older than 14 days, and a second rule to retain a maximum of 50 tagged images. Option D. Use an AWS Systems Manager automation runbook targeting the EC or repository to execute a daily cleanup script using the AWS execute script action. The answer here is option C. Create an Amazon EC or lifecycle policy containing 2 rules. One rule to expire untagged images older than 14 days, and a second rule to retain a maximum of 50 tagged images. This works because Amazon EC/R natively supports lifecycle policies designed exactly for this use case. EC/R lifecycle policies allow you to define JSON-based rules that evaluate image tags, tagged or untagged, image age, for example, older than 14 days, and image count, for example, retain 50. This fully managed feature requires zero maintenance once configured, providing the absolute lowest operational overhead. A. Writing and scheduling a custom Lambda function to interact with EC/R AP introduces unnecessary development and maintenance overhead when EC/R natively provides lifecycle policies. B. Users do not have direct access to the underlying AWS-managed S3 buckets that EC/R uses for storage, making standard S3 lifecycle policies impossible to apply to EC/R layers. D. Using Systems Manager automation to run cleanup scripts requires maintaining the script code and compute environment, which is inferior to using native managed lifecycle policies. Here's a useful exam tip. Always use Amazon EC/R lifecycle policies to automatically clean up old, untagged, or excessive container images. Avoid custom Lambda cleanup scripts. Question number 419. Scenario. A large enterprise uses AWS organizations to manage dozens of AWS accounts. Applications running on Amazon EC2 instances generate application logs, which are currently sent to Amazon CloudWatch logs within their respective local AWS accounts. The Security Operations Center, SOC, requires all application logs to be aggregated, searchable, and visualized in a single, dedicated centralized monitoring account. The logs must remain in CloudWatch. Which solution meets these requirements with the least operational overhead? Options. Option A. In the central monitoring account, configure CloudWatch cross-account observability. Define a monitoring account configuration and create a sync. Use an AWS CloudFormation stack set to deploy the required OEM Observability Access Manager. Link configuration to all source accounts in the organization. Option B. In the central monitoring account, provision an Amazon S3 bucket. In each source account, configure a CloudWatch log subscription filter that targets an Amazon Data Firehose delivery stream, configured to write cross-account into the centralized S3 bucket. Option C. Create an Amazon OpenSearch service domain in the central monitoring account. Deploy an AWS Lambda function in each source account triggered by CloudWatch logs metric streams to push the log data to the centralized OpenSearch endpoint via HTTPS. Option D. Install a secondary Amazon CloudWatch agent on all EC2 instances across the organization. Configure the secondary agent with IAM credentials that allow the logs. Put log events action directly against a unified log group in the central monitoring account. In this case, choose option A. In the central monitoring account, configure CloudWatch cross-account observability. Define a monitoring account configuration and create a sync. Use an AWS CloudFormation stack set to deploy the required OEM Observability Access Manager. Link configuration to all source accounts in the organization. Let's look at the reasoning. Amazon CloudWatch cross-account observability is the AWS native feature designed specifically to aggregate logs, metrics, and traces across an AWS organization into a central monitoring account without physically duplicating data. By configuring a sync in the central account and deploying the Observability Access Manager, OEM, links to the source accounts via CloudFormation stack sets, the SOC can natively search and visualize logs across the entire organization. The other choices do not work because B. Using subscription filters and Firehose to stream data to S3 removes the logs from the CloudWatch interface, violating the requirement that the data must remain searchable in CloudWatch. C. Creating an OpenSearch cluster and using Lambda to push logs introduces massive operational complexity and cost and moves the data out of CloudWatch. D. Installing secondary CloudWatch agents and pushing logs directly cross-account is operationally brittle and difficult to maintain securely at an enterprise scale compared to native OEM linking. The main takeaway is when asked to centralize visibility of CloudWatch logs, metrics, or traces across multiple AWS accounts while keeping the data within the CloudWatch service. Use CloudWatch cross-account observability, OEM. Next, question number 420. We're moving on to secrets management. A company manages its AWS environments using a multi-account strategy. A continuous integration and continuous deployment, CI/CD, pipeline running in a deployment account requires a highly sensitive database password to perform automated database migrations. Security policies mandate that all sensitive credentials must be stored centrally in a dedicated security account, encrypted using keys managed by the company and accessed directly by the pipeline across account boundaries without hard-coding or duplicating the secrets. Which combination of steps will meet these requirements? Choose 3. More than one answer may be correct. Option A. Store the database password in AWS Secrets Manager within the security account. Option B. Store the database password as a standard tier secure string in AWS Systems Manager parameter store within the security account. Option C. Encrypt the secret using a customer-managed AWS KMS key in the security account. Grant the CI/CD IAM role in the deployment account KMS. Decrypt permissions on the key. Option D. Share the secret with the deployment account by utilizing an AWS Resource Access Manager, AWS RAM, Resource Share. Option E. Attach a resource-based policy to the secret in the security account explicitly granting the CI/CD IAM role in the deployment account permissions to retrieve the secret value. Option F. Configure the CI/CD pipeline to assume an AWS IAM user in the security account and pass the user's access keys as pipeline environment variables. You should choose option A. Store the database password in AWS Secrets Manager within the security account. Option C. Encrypt the secret using a customer-managed AWS KMS key in the security account. Grant the CI/CD IAM role in the deployment account KMS. Decrypt permissions on the key. And option E. Attach a resource-based policy to the secret in the security account, explicitly granting the CI/CD IAM role in the deployment account permissions to retrieve the secret value. AWS Secrets Manager supports cross-account access through a resource-based policy on the secret. Because the secret is encrypted with a customer-managed KMS key in the security account, the cross-account CI/CD role also needs the required KMS permissions, and the KMS key policy must allow that external principal. Therefore, it stores the credentials centrally. C provides decrypt authorization for the company-managed key, and E grants the role permission to retrieve the secret without duplicating it. Now let's rule out the other options. B. Standard tier parameter store parameters cannot be shared across accounts. Parameter store now supports cross-account sharing for advanced tier parameters, including secure string parameters when a customer-managed KMS key is shared appropriately, but that is not what option B specifies. D. AWS RAM is the sharing mechanism for eligible advanced tier parameter store parameters, not for an AWS Secrets Manager secret selected in option A. F. Long-term IAM user access keys in pipeline environment variables violate the requirement to avoid hard-coded or duplicated credentials and are inferior to role-based access. Keep this point in mind for the exam. For cross-account Secrets Manager access, combine a secret resource policy, permission on the calling role, and access to the customer-managed KMS key. Parameter store cross-account sharing is available only for advanced tier parameters. Question number 421. Let's go. A company runs an asynchronous data processing application on Amazon Elastic Container Service, Amazon ECS, using AWS Fargate. The application pulls an Amazon Simple Queue service, Amazon SQS, queue for tasks. Processing a single task takes approximately 5 minutes. Traffic to the SQS queue is highly unpredictable. Most of the time, the queue is empty, but occasionally it receives sudden bursts of thousands of messages. During these bursts, messages sit in the queue for hours before being processed, leading to missed business SLAs. A DevOps engineer must ensure the application scales aggressively to handle bursts while minimizing idle compute costs during quiet periods. Which solution will meet these requirements most cost-effectively? Option A. Configure the Amazon SQS queue to push messages directly to an Amazon EventBridge event bus. Create an EventBridge rule that uses the ECS Run Task API to launch a new Fargate task for every matched event. Option B. Migrate the ECS cluster from AWS Fargate to Amazon EC2 instances. Use an auto-scaling group for the EC2 instances with a simple scaling policy triggered by CPU utilization above 80%. Option C. Register the ECS service as a scalable target with AWS Application Auto-Scaling. Configure a target tracking scaling policy using a custom CloudWatch metric based on the SQS queue's approximate number of messages visible per task. Option D. Modify the application code to use SQS long polling. Increase the max number of messages requested per API call to 10 to process tasks in parallel within the existing running containers. Go with option C. Register the ECS service as a scalable target with AWS Application Auto-Scaling. Configure a target tracking scaling policy using a custom CloudWatch metric based on the SQS queue's approximate number of messages visible per task. Here's why. When scaling a worker fleet based on an SQS queue backlog, CPU and memory metrics are unreliable indicators of scale. The most effective approach is to use AWS Application Auto-Scaling with a target tracking policy based on the acceptable backlog per task, for example, approximate number of messages visible / running capacity. This ensures the Fargate tasks scale aggressively during bursts and scale and to minimize costs when the queue empties. The remaining options can be eliminated because A. EventBridge rules triggering ECS run task directly creates unbounded, unmanaged tasks that are not governed by an ECS service, risking API throttling and out-of-control costs during large bursts. B. Scaling EC2 instances on CPU utilization does not reflect the depth of an SQS. CPU might be low while thousands of messages are backlogged. D. Increasing max number of messages to 10 improves single-task throughput, but does not scale out the compute capacity to handle sudden bursts of thousands of tasks that take 5 minutes each. When processing asynchronous tasks from Amazon SQS on ECS or EC2, always scale based on the queue depth, approximate number of messages visible divided by the number of instances/tasks, not CPU or memory. Here comes question number 422. Consider this situation. A gaming company is developing a cross-platform mobile application. The development team uses AWS code pipeline to orchestrate builds and deployments. Before a release candidate can be deployed to production, it must pass a suite of automated UI and performance tests running concurrently across dozens of different physical Android and iOS devices. The testing solution must scale automatically to handle multiple concurrent pipeline executions. Which solution meets these testing requirements with the least management overhead? Here are the options. Choice A. Provision a cluster of Mac bare metal Amazon EC2 instances. Install mobile device emulators in Jenkins on the instances, and configure code pipeline to trigger the Jenkins test jobs via a webhook. Choice B. Package the mobile test suite in a Docker container. Configure an AWS code build project within the pipeline to run the container using AWS Fargate to execute simulated browser tests. Choice C. Add an AWS device farm test action to the code pipeline. Configure device farm to run the automated test suite across a managed device pool containing the required physical mobile devices. Choice D. Use AWS Lambda functions with custom runtime environments to execute the mobile test binaries. Trigger the Lambda functions synchronously from a pipeline stage using an invoke action. The best choice is option C. Add an AWS device farm test action to the code pipeline. Configure device farm to run the automated test suite across a managed device pool containing the required physical mobile devices. This is the best choice because AWS device farm is a fully managed app testing service that allows developers to test Android, iOS, and web apps on real, physical phones and tablets hosted by AWS. AWS code pipeline provides native integration with device farm as a test action. This completely removes the overhead of managing local emulators or physical device labs. Let's quickly check the incorrect choices. A. Provisioning Mac EC2 instances and installing Jenkins with device emulators introduces immense operational overhead for infrastructure maintenance and patching. B. Docker containers running on AWS Fargate cannot accurately simulate native mobile device hardware, like iOS environments, for physical performance testing. D. AWS Lambda is a serverless compute service for running functions. It does not provide mobile device environments or graphical emulation for UI testing. Exam tip. Whenever a scenario asks for automated UI and performance testing on physical iOS and Android devices integrated with a CI/CD pipeline, AWS device farm is the correct managed service. Next, question number 423. Scenario. A company operates dozens of Amazon Elastic Kubernetes Service, Amazon EKS, clusters. Currently, a cloud engineer creates and manages these clusters manually by executing AWS CLI commands, AWS X create cluster, and AWS X create add-in from a local terminal. The company is struggling to keep the Kubernetes control plane and manage node groups updated before they reach the end of standard support. A DevOps engineer must implement a predictable, repeatable, and easily auditable process for provisioning and upgrading the EKS clusters. Which solution will meet these requirements with the least operational overhead moving forward? Options. Option A. Write a bash script that iterates over all cluster ARNs and automatically executes the AWS X update cluster version command. Schedule the script to run monthly using a cron job on a persistent Amazon EC2 instance. Option B. Refactor the cluster provisioning process to use an infrastructure as code tools such as AWS CloudFormation or Terraform. Perform future Kubernetes version upgrades by updating the version parameter in the declarative code and deploying the change via a CI/CD pipeline. Option C. Enable EKS auto mode on all clusters so that AWS fully manages the control plane version upgrades, and delete all existing managed node groups to rely exclusively on AWS Fargate. Option D. Create an AWS Systems Manager maintenance window. Configure an automation runbook task using the AWS Support Upgrade Cast Cluster document to automatically perform in-place upgrades across the fleet when versions become deprecated. In this case, choose option B. Refactor the cluster provisioning process to use an infrastructure as code tools such as AWS CloudFormation or Terraform. Perform future Kubernetes version upgrades by updating the version parameter in the declarative code and deploying the change via a CI/CD pipeline. The main reason is managing complex infrastructure like EKS clusters via manual CLI commands is unscalable and prone to human error. Refactoring to an infrastructure as code approach ensures that the cluster definitions, add-ons, and node groups are version controlled. Upgrading clusters simply involves updating the version string in the infrastructure as code template and pushing to a CI/CD pipeline, providing predictable, auditable updates with the least long-term operational overhead. Here's why the alternatives are not suitable. A cron job running a bash script to blindly update cluster versions is extremely dangerous. It lacks error handling, peer review, and rollback capabilities. C. EKS auto mode simplifies node management, but the user is still ultimately responsible for initiating the control plane version upgrades. AWS does not forcibly upgrade non-deprecated control planes automatically without customer consent. D. Systems Manager does not have a native AWS Support Upgrade Cast Cluster automation document specifically for safely upgrading entire EKS clusters seamlessly. A helpful shortcut is this. Manual AWS CLI commands are an anti-pattern for production infrastructure. Always migrate manual provisioning to infrastructure as code, CloudFormation, CDK, or Terraform to enable repeatable, auditable lifecycle management. Question number 424. A software company wants to enforce a strict least privilege security model using attribute-based access control, ABAC. The company uses AWS IAM Identity Center to manage access to its AWS accounts. The company requires that developers can only manage Amazon EC2 instances and database administrators, DBAs, can only manage Amazon RDS databases. Furthermore, employees should only be able to interact with infrastructure that belongs to the specific project they are assigned to. All AWS resources are consistently tagged with a project key. Which combination of steps will successfully implement this ABAC model? Choose 3. Choose every option that satisfies the requirement. Choices. Option A. Configure the identity provider connected to IAM Identity Center to pass the user's assigned project and job function attributes as session tags during authentication. Option B. Create separate IAM roles for every single project in the company and manually assign users to the specific roles they need via IAM groups. Option C. Create an IAM Identity Center permission set for developers granting EC2 permissions and a separate permission set for DBAs granting RDS permissions. Option D. Attach customer-managed IAM policies to the permission sets that include a condition explicitly allowing actions only when the AWS resource tag/project key matches the AWS principal tag/project key. Option E. Use AWS Resource Access Manager, AWS RAM, to share specific EC2 and RDS resource ARNs directly with the individual IAM Identity Center user identities. Option F. Apply a service control policy, SCP, to the organization that denies all actions unless the principal ARN explicitly contains the string developer or DBA. The required selections are Option A. Configure the identity provider connected to IAM Identity Center to pass the user's assigned project and job function attributes as session tags during authentication. Option C. Create an IAM Identity Center permission set for developers granting EC2 permissions and a separate permission set for DBAs granting RDS permissions. And Option D. Attach customer-managed IAM policies to the permission sets that include a condition explicitly allowing actions only when the AWS resource tag/project key matches the AWS principal tag/project key. This works because this is the standard architectural pattern for attribute-based access control, ABAC, in AWS. By mapping attributes from the IDP as session tags. A. The AWS session knows the user's project context, principal tag, grouping users into job function permission sets. C. Establishes the baseline resource type permissions. Finally, enforcing the tag matching condition. D. Dynamically restricts the user to interact only with resources that share their project tag, satisfying all requirements without creating a role per project. B. Creating an IAM role for every single project is role-based access control, or BAC, which scales poorly and directly violates the efficiency goal of ABAC. E. AWS Resource Access Manager, RAM, is used to share specific AWS resources, like subnets or transit gateways, across accounts. It is not used to grant EC2/RDS management access to IAM identities. F. Using an SCP to restrict actions based on a string in the principal ARN is fragile and doesn't handle the project-level resource restrictions required by the scenario. Here's a useful exam tip. Attribute-based access control, ABAC, scales better than our BAC. It relies on mapping identity attributes to AWS session tags, principal tag, and using IAM conditions to compare AWS resource tag to AWS principal tag. Question number 425. Treat this as an easy question. Scenario. A company uses AWS code deploy to orchestrate in-place application updates on an Amazon EC2 auto-scaling fleet. During a recent production release, the deployment failed on several instances during the before-install lifecycle event. A DevOps engineer needs to identify the exact error output generated by the application lifecycle scripts to determine the root cause of the failure. The engineer needs to do this quickly without relying on SSH access to individual instances. What is the most operationally efficient way to analyze the detailed deployment lifecycle errors? Option A. Install the Amazon CloudWatch agent on the EC2 instances. Configure the agent to monitor the /opt/codedeploy agent, /deployment route, /deployment logs, /directory, and stream the code deploy agent logs to CloudWatch logs. Query the logs using CloudWatch logs insights. Option B. Update the application's appspec.yml file to include a hooks section that automatically zips the /log/messages directory and uploads it to an Amazon S3 bucket upon a deployment failure. Option C. Navigate to the AWS Code Deploy console, locate the failed deployment ID, and view the aggregated AWS CloudTrail data events to read the standard error output of the deployment scripts. Option D. Use AWS Systems Manager Session Manager to establish an interactive shell session with each failed EC2 instance. Navigate to the /var/log/aws/codedeploy agent/directory and manually search the files using grep. The right response is Option A. Install the Amazon CloudWatch agent on the EC2 instances. Configure the agent to monitor the /opt/codedeploy agent, /deployment route, /deployment logs/directory, and stream the code deploy agent logs to CloudWatch logs. Query the logs using CloudWatch logs insights. Let's look at the reasoning. The AWS code deploy agent logs all deployment lifecycle execution errors to files within the /opt/codedeploy agent, /deployment route, /directory on the local instance. By installing the CloudWatch agent and streaming these logs to CloudWatch logs, DevOps engineers can centrally query and analyze the exact script output across the entire fleet instantly using CloudWatch logs insights, avoiding manual SSH/SSM access. The other choices do not work because B. Modifying the application deployment hooks to manually zip logs and push to S3 on failure is complex custom orchestration. Furthermore, /var/log/messages contains system logs, not code deploy script execution output. C. AWS CloudTrail only logs control plane API calls, for example, who initiated the code deploy deployment. It does not log the standard output of shell scripts running locally on the EC2 instances. D. While Systems Manager Session Manager is better than SSH, manually logging into every single failed instance and grepping log files does not scale and is operationally inefficient compared to centralized log querying. The main takeaway is to centrally monitor and troubleshoot AWS code deploy errors on EC2 without logging into instances. Stream the code deploy agent logs, codedeployagent.log and script outputs to Amazon CloudWatch logs using the CloudWatch agent. Now for question number 426. Consider this situation. A financial technology company operates a highly sensitive serverless application built using Amazon API Gateway, AWS Lambda, and Amazon DynamoDB. The security team is concerned about potential software supply chain attacks where malicious code could be introduced into the Lambda functions during the CI/CD pipeline process. The team needs an automated security capability that continuously monitors the runtime behavior of the deployed Lambda functions and detects anomalous network activity, such as a function attempting to contact a known malicious command and control server. Which solution will meet these detection requirements? The choices are: Option A, associate an AWS WAF Web ACL with the API Gateway REST API. Configure a managed rule group specifically targeting malicious IP addresses and anomalous request patterns. Option B, enable Amazon Guard Duty in the AWS account and enable Guard Duty Lambda protection so Guard Duty analyzes Lambda network activity logs, including VPC flow log-derived activity from the functions, for suspicious outbound communication such as connections to known malicious servers. Option C, integrate AWS code build into the CI/CD pipeline. Configure a build stage that uses AWS CloudFormation Guard to scan the Lambda deployment package for known CVs before deployment. Option D, deploy an AWS network firewall in the VPC where the Lambda functions execute. Configure a stateful rule group using Suricata rules to block outbound traffic to untrusted domains. The answer here is option B. Enable Amazon Guard Duty in the AWS account and enable Guard Duty Lambda protection so Guard Duty analyzes Lambda network activity logs, including VPC flow log-derived activity from the functions, for suspicious outbound communication such as connections to known malicious servers. Guard Duty Lambda protection is the managed runtime threat detection capability designed for Lambda network activity. When enabled, Guard Duty analyzes Lambda network activity logs, including VPC flow log-derived activity from Lambda functions, and can generate findings for suspicious communication such as contact with malicious servers. It does not require an agent inside the function or custom detection rules. Now let's rule out the other options. A, AWS WAF protects inbound web requests at API Gateway. It does not provide runtime threat detection for outbound Lambda network behavior. C, CloudFormation Guard validates infrastructure as code policies and is not a CVE scanner or runtime behavior monitor for Lambda packages. D, Network Firewall can enforce network rules for VPC traffic, but it is an enforcement service that requires network architecture and rule management. Guard Duty Lambda protection provides the requested managed threat detection with lower operational overhead. Keep this point in mind for the exam. Use Guard Duty Lambda protection for managed detection of suspicious Lambda network behavior. Do not assume Lambda protection currently consumes every possible network signal, such as Lambda-generated DNS data, unless current documentation explicitly says so. Question number 427. Let's go. A company has a suite of AWS Lambda functions that were created manually via the AWS Management Console over several years. The company is adopting the AWS Cloud Development Kit, AWS CDK, using Python for all infrastructure management. A DevOps engineer must bring the existing manual Lambda functions under CDK control. The goal is to generate the corresponding CDK Python code for the existing infrastructure with the absolute minimum amount of manual coding. Which solution will meet this requirement with the least implementation effort? Choices. Option A. Use the AWS CloudFormation infrastructure as code generator to perform a resource scan and generate a CloudFormation template. Manually define matching L1 constructs in a new CDK application and run CDK import for each existing Lambda function. Option B. Query AWS config using an advanced query to extract the JSON configuration of all Lambda functions. Write a Python script to parse the JSON and map the parameters directly into AWS_Lambda function CDK constructs. Option C. Enable AWS CloudTrail and search for the original create function API events. Extract the request payload parameters and manually translate them into CDK Python code. Option D. Run the AWS CDK CLI/CDK migrate command with from scan, language Python, and filters for the Lambda resources. Let CDK migrate use the CloudFormation infrastructure as code generator to scan the deployed unmanaged resources. Generate a new Python CDK application with L1 constructs and import the existing resources when the new stack is first deployed. Resolve any reported write-only Lambda properties, such as code asset locations, before deployment. Go with option D. Run the AWS CDK migrate command with from scan, language Python, and filters for the Lambda resources. Let CDK migrate use the cloud formation infrastructure as code generator to scan the deployed unmanaged resources, generate a new Python CDK application with L1 constructs, and import the existing resources when the new stack is first deployed. Resolve any reported write-only Lambda properties, such as code asset locations, before deployment. Here's why. CDK migrate can migrate deployed resources that are not associated with a cloud formation stack. With from scan, the CDK CLI invokes the cloud formation infrastructure as code generator, creates a new CDK app, generates L1 constructs, and uses migration metadata to associate the existing resources with the new cloud formation stack when deployed. The language option can generate Python and filter can restrict the scan to the target Lambda resources. Some Lambda properties are write-only, so asset values may still require targeted manual resolution, but this is the lowest coding supported path. The remaining options can be eliminated because A. Infrastructure as code generator plus manually defining L1 constructs, and CDK import duplicates work that CDK migrate automates. CDK import requires the resources to be defined in the CDK app first. B. Converting AWS config JSON to CDK constructs with custom code is a manual, error-prone implementation. C. CloudTrail event history is not a durable reconstruction source for years-old resources, and manually translating API payloads into CDK code creates substantial effort. For unmanaged deployed resources that must become a new CDK app, use CDK migrate from scan. CDK migrate generates L1 constructs and may require you to fill in write-only properties such as Lambda code assets. Question number 428. Here's what is happening. A company runs a specialized, stateful legacy application on a single Amazon EC2 instance backed by Amazon Elastic Block Store, Amazon EBS. Due to the application's licensing model, it cannot be run across multiple instances or placed behind a load balancer. The company wants to improve resilience against underlying AWS hardware failures. If the physical host supporting the instance loses network connectivity or power, the EC2 instance must automatically reboot on healthy hardware while retaining its instance ID, IP address, and attached EBS volumes. Which solution meets these automated recovery requirements? Here are the options. Choice A. Place the EC2 instance in an Amazon EC2 auto-scaling group with the minimum, maximum, and desired capacity set to 1. Configure the group to use EC2 health checks. Choice B. Create an Amazon CloudWatch alarm monitoring the status check failed _instance metric. Configure the alarm to execute an EC2 auto recovery action when the alarm enters the alarm state. Choice C. Create an Amazon CloudWatch alarm monitoring the status check failed _system metric. Configure the alarm to execute an EC2 auto recovery action when the alarm enters the alarm state. Choice D. Enable Amazon Route 53 Application Recovery Controller, ARC. Configure a routing control to automatically restart the EC2 instance in a different availability zone if a failure is detected. The best choice is option C. Create an Amazon CloudWatch alarm monitoring the status check failed _system metric. Configure the alarm to execute an EC2 auto recovery action when the alarm enters the alarm state. This is the best choice because Amazon EC2 features 2 status checks, instance and system. A system status check failure, status check failed _system, indicates an underlying AWS hardware or network failure. By configuring a CloudWatch alarm with an EC2 auto recovery action, AWS will automatically migrate the instance to healthy underlying hardware while strictly retaining the exact instance ID, private IP addresses, elastic IP addresses, and all attached EBS volume data, perfectly satisfying the legacy application's requirements. Let's quickly check the incorrect choices. A. Using an auto-scaling group with a capacity of 1 will terminate the impaired instance and launch a completely new instance with a new instance ID and fresh EBS volumes, destroying the stateful data. B. Status check failed _instance indicates OS level issues, for example, kernel panic, high CPU. While auto recovery can reboot it, the prompt specifically specifies underlying physical host hardware/network issues, which correlate to system checks. D. Route 53 ARC is used to failover traffic routing between distinct AWS regions or availability zones for multi-availability zone application architectures. It does not reboot individual EC2 instances. Exam tip. To automatically recover a stateful EC2 instance due to underlying AWS hardware failures while preserving the instance ID, IP addresses, and EBS data, use a CloudWatch alarm on status check failed_system with the EC2 recover action. Next, question number 429. Scenario. A global financial firm stores millions of critical transaction receipts in an Amazon S3 bucket in the US East 1 region. To meet stringent disaster recovery requirements, the firm creates a secondary S3 bucket in the US West 2 region and configures two-way cross-region replication. The compliance team requires the AWS SLA-backed replication capability designed to replicate 99.99% of new objects within 15 minutes and requires replication metrics for verification. The application must use a single global S3 endpoint, and the operations team must be able to manually fail over data request routing from the primary region to the secondary region during a disaster. Which combination of steps will implement this disaster recovery strategy? Choose 3. Select all answers that apply. Options. Option A. Enable S3 replication time control, S3 RDC, on the replication rules configured for both the primary and secondary S3 buckets. Option B. Configure an S3 multi-region access point in an active-passive configuration spanning both the US East 1 and US West 2 buckets. Option C. Enable Amazon S3 transfer acceleration on both buckets to ensure that cross-region object copying completes within the required time window. Option D. Use the Amazon S3 multi-region access point failover controls to set the normal routing state to US East 1 active and US West 2 passive, and change the routing states during a disaster to shift requests to US West 2. E. Use AWS Global Accelerator to create a custom endpoint that balances traffic based on backend S3 bucket latency. F. Configure an Amazon Event Bridge rule to invoke an AWS Lambda function every minute to monitor replication latency and force synchronization if it exceeds 10 minutes. The answers that work here are Option A. Enable S3 replication time control, S3 RDC, on the replication rules configured for both the primary and secondary S3 buckets. Option B. Configure an S3 multi-region access point in an active-passive configuration spanning both the US East 1 and US West 2 buckets. And Option D. Use the Amazon S3 multi-region access point failover controls to set the normal routing state to US East 1 active and US West 2 passive, and change the routing states during a disaster to shift requests to US West 2. The main reason is S3 replication time control provides the SLA-backed replication tier that replicates 99.99% of new objects within 15 minutes and exposes replication metrics. An S3 multi-region access point provides a single global S3 endpoint. In an active-passive multi-region access point configuration, native S3 failover controls let operators change regional routing states and redirect data requests from the active region to the passive region during disaster recovery. These capabilities directly satisfy the replication, unified endpoint, and manual failover requirements. Here's why the alternatives are not suitable. C. S3 transfer acceleration optimizes client transfers into S3. It does not provide the replication time SLA for CRR. E. Applications should use the S3 multi-region access point endpoint. Global Accelerator is not configured as a custom load balancer directly in front of S3 buckets for this requirement. F. A Lambda function cannot force S3 replication to complete. S3 RDC is the managed mechanism for predictable replication time and monitoring. A helpful shortcut is this. Use S3 RDC for SLA-backed 15-minute replication performance and S3 multi-region access point failover controls for active-passive S3 request failover. Route 53 ARC is not required to control MRAP routing. You have completed set 23 of the DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. How did you score? Share your result in the comments. Work through all the sets to build broader exam readiness and cover more practice questions. Please like this video, subscribe to Tech with Kaushik, and enable notifications for more certification exam preparation content. Thank you for watching, and I will see you in another practice set.